Okay, welcome to lesson 6.3, exploring graphs of primary trigonometric functions. This lesson is an investigation, so normally in class I would give this to you to work on your own, and I would just quickly take it up. So I'm going to walk through it, but feel free to give it a shot on your own, and then just watch the video for the answers. We're going to use our knowledge of special angles from our special triangles and from our 6.2 warm-up to complete the tables below. So we're going to be looking at the graphs of sine theta in the first table and then cos theta in the second table. So cos theta, we're looking at, here I'm given the angle of sine theta, here I'm given the angle of 0 degrees. Remember that sine theta is the y value as I'm rotating around the circle. So at 0, the sine value or the y value, if I was sitting on the positive x-axis, would be 0. And then if I scroll around to pi by 4, so now I'm in the pi by 4 triangle. I'm thinking about that triangle. Sine theta would be the opposite over the hypotenuse. So 1 over root 2, but in simplest form, that's root 2 over 2. And then up at pi by 2, now I'm on the now I'm on the positive y-axis as I'm rotating around the circle. So I'm kind of switching between rotating around the circle and thinking about the special triangles. So here I'm thinking about being here in my rotation, and there my y value, remember sine theta is equal to the y value if I'm in the unit circle with a radius of 1, the y value will be 1. And then here I'm going to be thinking about 3 pi by 4. So then I'm thinking about taking the top of my circle, cutting it into 4 wedges and getting to the third wedge. So there would be my angle theta. My beta, my related acute angle down in here, would be pi by 4 because I'm missing one of the 4 wedges. So now I'm still in the pi by 4 triangle, so I'm still looking at root 2 over 2. I just have to think about, is it positive or negative in this quadrant? So I'm in the CAS quadrant, and so my ratio is still positive since I'm looking at sine. Then moving over to pi, so now I'm thinking about rotating over here to this negative x-axis. Again, the sine of theta is equal to the y value. So the y value, if I was sitting on the negative x-axis, would be 0. Then going over to 5 pi by 4, so again I'm cutting the top into 4 wedges, the bottom into 4 wedges. I need to count around to 5 of them, so it's going to be this terminal arm right here. And again, my beta, my related acute angle, would be pi by 4, so my ratio is going to be root 2 over 2, and I just have to think about, is it positive or negative? So I'd be in the CAST quadrant, so I'm in the T quadrant, that means the sine ratio is negative. Then the other way to think about that is that the y values are negative down here, and sine theta is y over the radius, so the y value is going to be negative. The radius can never be negative. Next I'm looking at 3 pi by 2, which we know is our negative y-axis. There I am right here. And for that one, again, I'm thinking about the sine value is 0, or sorry, the sine value is the y value, and the radius of the circle is 1. So here the y value would be negative 1 if I was on a unit circle. And then 7 pi by 4, again, 4 wedges on the top, 4 wedges on the bottom, and I'm counting around until I get to 7 of them. There I am right there. So again, my related acute angle beta would be pi by 4, so I'm looking at root 2 over 2, and I'm just asking myself, is it positive or negative? I'm in the C quadrant, so the sine ratio is negative. And then coming right back around full circle to 2 pi, well, that's just the same as being at 0 rotation, so again, my y value is 0 at that point. Now we're going to graph this. So some of these values are really easy to graph, and we can quickly see all of those exact values. Those are what we call key points on the graph. But these other ones are just going to add a little bit of information for us. So what I'm going to do is just quickly type that into my calculator, root 2 over 2, or you could type sine of pi by 4 into your calculator, making sure you're in radian mode. So again, I'm going to change that. I'm just using 2 decimal places because I'm graphing. I want to just kind of know about where is the height of this thing. And now all of these fractions are the same, it's just the sign is changing. All right, next we're going to take a look at the cosine graph. So the cosine, you might remember, is the x if I was thinking about rotating around the circle. So here, when I'm thinking about rotating nowhere around the circle, I'm here on the positive x-axis. If I was on the unit circle, then the x value would be 1. And then if I was thinking about rotating to pi by 4, thinking about my pi by 4 triangle, the cosine ratio is the same as the sine ratio. since the adjacent and the opposite are the same in that triangle. Then rotating around to pi by 2. And you can be using your calculator to help you with some of these, but hopefully you're getting in the habit of remembering your special triangles, remembering the rotating around the circle, thinking about those two things together, and connecting it with graphing, right? It's all related to each other. Here I'm rotating to pi by 2, and here again cosine is my x value, so my x value at that point will be 0. Then rotating to 3 pi by 4, so here I am in this quadrant. My related acute angle is pi by 4, so the ratio is root 2 over 2, but I'm in the CAS quadrant, so cosine is negative. Then rotating to pi. Ooh. Technical difficulties. Then rotating to pi. There we are. Thinking about cosine is my x value, so I'm over at -1. Next, looking at 5 pi by 4, 4 pi by 4 is on the top, and 1 passed. So there I am in the CAST quadrant. It's going to be negative, and it's root 2 over 2. Remember, cosine is the x value, so it makes sense that when I'm over here on the left side of the y-axis, my x values are negative and my cosine ratios are negative. That's why the CAST rule works. So hopefully you've looked at that maybe in grade 11. Next, we're going to take a look at 3 pi by 2. So I'm rotating all the way around to that bottom, or the negative y-axis. Again, cosine is my x value, so it's 0. And then 7 pi by 4, here I am, 7/8 of the way around the circle. Remember, 4 wedges on top, 4 wedges on bottom. And again, my related acute angle is pi by 4, so it's root 2 over 2. I'm in the C quadrant this time, so cosine is positive. And then 2 pi at the end, that's the same as rotating 0 the same as rotating to 0 radians, but remember at 0 radians or at 2 pi, the x value is 1. All right, we're going to convert these guys to decimals as well, but it's the same as the sign ratio. Just the signs, positive and negatives, are changing. All right, we're going to quickly graph the sine curve and the cosine curve, so you can use two different colors if you want. I'm going to put them both on the same graph here. I'm going to start with the sine curve. The sine curve, and oops. What is happening? Okay, the sine curve starts at the origin, and then it does end at 2 pi, right? The period is 2 pi. Remember that the sine curve goes up to the maximum, then hits the axis again, down to the minimum, and then returns to the axis. And we did see that in our table, that sine of theta was 0 at 0, pi, and 2 pi. So when we get here, this is pi by 2, because we're halfway to pi. So at pi by 2, I'm going to hit the maximum. So there's no y-axis here. You can make it as tall as you want. We know that the maximum value of the sine curve and the cosine curve is 1, and the minimum is -1. But you can put them however high you want. When I am at pi by 2, I have a y value of 1. And when I'm at 3 pi by 2, that's this value right here, I'm at -1. And we can kind of already see that sine curve happening. Now we also know that pi by 4, so remember if this is pi by 2, pi by 4 is another, cut that guy in half. So there's pi by 4, halfway, there would be 3 pi by 4. So all of these kind of halfway points are also in our table. Now remember that this is 0.7. So I've drawn my 1 at 4 squares, so 3 squares would be 0.75. I need to get to 0.71, so it's just below this. And then here at 3 pi by 4, the sine curve is also positive, and then we flip to negative, so just below 0.75 or above on the negative side. And so I can add those in as well. When you're drawing your sine curve, one of the things you want to think about is it's not a triangle. So you're not like heading straight for that point. It's actually kind of flat at the top and at the bottom. So if you want to draw those flat points in, it sometimes helps people create a smooth curve. And then you're just going to continue this pattern as you go along. Remember, my expectation is that you can graph the max, mins, and axis values. So I'm not as concerned about graphing those pi by 4 values. And then we'll repeat the same pattern going backwards. So I like to just add those max, min, and axis values as we go along. Oops. Don't forget arrows on the end because that sine curve goes on forever. All right, so there's my sine theta. I'm going to label using color. You can label each of the graphs if you want. I'm going to do cos theta next. So my cosine curve actually starts on the y-axis at a height of 1. And then from there, again, I'm rotating to the axis, then to -1 at pi, to the axis, and then back up to 1 at 2 pi. So I should see that I'm back at the same spot 2 pi later. And then I just continue to rotate in that fashion. I'm kind of thinking about rotating around that wheel or that unit circle as I draw this. I'm always connecting those two ideas. It helps me have a fuller understanding. When you draw the sine curve, oops, that's not good. When you draw the sine curve, you could be thinking about the height along the wheel, and then the cosine is actually the horizontal distance when you're on the wheel. The horizontal distance from the center. All right, there's our cosine curve. All right, so we're going to talk about properties, or sometimes we call these the characteristics. So you'll see that word as well. When they ask you to state the characteristics or state the properties, we're talking about these trigonometric words like period, axis, amplitude, that kind of thing. So for sine and cosine, a lot of these properties are the same. So what we notice here, the period, that's the length it takes for one cycle. You might remember that term from our 6.0 review or from grade 11. It's the period of this curve, how long it takes for one complete cycle, that's 2 pi. And you remember that from grade 11, it was 360 degrees. The axis is always an equation. So I'm looking for you to state the full equation here, not just half of it. The axis of the curve is the line that goes through the center of the curve. So it's that horizontal, or sorry, the vertical center. It's a horizontal line that cuts it vertically in half. And so for the parent functions, y equals sine 0 or sine theta and y equals cos theta, the axis of the curve is y equals 0. That might move around as we do some transformations on these curves. The amplitude of my base curve, so remember the amplitude is the distance from that axis to the top, oops, from the axis to the top of the curve, there's my amplitude, or I could be thinking about it as from the axis to the bottom of my curve. So I've drawn the amplitude on the sine curve both times there, but you can see it's the same on the cosine curve. In either case, it's a distance of 1. So it's just a vertical distance that we're looking for. The amplitude can never be negative because it is a distance. All right, so what about the maximum value on the curve? So when we talk about the maximum value, we're talking about the maximum y value. So when I look at either one of these curves, you can see that the maximum height of the curve is 1 and the minimum height of the curve is -1. Now it's going to change again as you do some transformations. Right? If I vertically stretch that or vertically shift that, then those y values will change. All right, so what about domain and range? The domain of any trig function, or sorry, any sine or cosine curve is going to be the set of all thetas belonging to the set of real numbers. And sometimes they use theta in here for your dependent or for your independent variable, and sometimes they'll use x, so then I would change that to an x. And then for my range, y belongs to a set of real numbers, and there's definitely some limitations on our range. Our range is bouncing between -1 or 1, or the mathematical term would be oscillating between -1 and 1. And of course, we want less than or equal to signs because it can actually equal 1. All right, flipping that over to the back, let's learn something kind of new. We're going to look at the tan curve. So first, again, we're coming up with these values. You can use your calculator, or for better practice, thinking about our special triangles and rotating around the axis. Remember that when I'm rotating around, tan theta is equal to the y value over the x value of the point on the terminal arm. So when I rotate, when I start at 0, I'm thinking about the y value. So I'm thinking about being on this terminal arm here. The y value of this point would be 0, and the x value would be 1. So again, tan theta is the y divided by the x. 0 divided by 1 is just 0. And then thinking about rotating to pi by 4, there's my pi by 4. That's going to be my 1, 1, root 2 triangle. And so the opposite over the adjacent for tan is 1 over 1, or 1. Then we're rotating to pi by 2, thinking about my terminal, being on my terminal arm. So now I'm thinking about tan theta as being the y divided by the x of this point here. So that'd be 1 divided by 0. That's undefined. So this graph is definitely going to look different than the sine and the cosine curve, right? This guy's a weirdo. Next, we're looking at 3 pi by 4. So again, rotating around here, 3/4 of the way across the top. 3 pi by 4, I'm looking at my beta as being pi by 4. So I'm going to have the 1 over 1. But I need to think about, is it positive or negative? So I'm in the CAS quadrant, so it's going to be -1. Next, rotating to pi. When I'm at pi, I'm thinking about tan as being the y value divided by the x value. So here, again, my y value is 0, and my x value is -1. 0 divided by -1. Then rotating to 5 pi by 4, there I am. I'm thinking about my pi by 4 triangle, so I know that opposite over adjacent is 1, and then I'm in the CAST quadrant, so this one is actually positive. Then rotating to 3 pi by 2. It's at negative y-axis, so thinking about the value of this point here, my x value is 0 and my y value is -1. So when I do -1 divided by 0 for my opposite over adjacent, I get undefined. Then 7 pi by 4, so going 7/8 around the circle, 4 on top, and then 3/4 of the way across the bottom. My related acute angle is again pi by 4, so I know that the value is 1, but I'm in the C quadrant, so it's -1 because I'm looking at tan. And then for 2 pi, again, thinking about rotating all the way around the circle, at this point here, the x value is 1, and the y value is 0, so I do 0 divided by 1, and I get a tan value of 0. No decimal conversions for these guys here, all nice points for me. So what does this look like? That's the question, right? So I know that at 0 it's here. At pi by 2 it said it's undefined. And then at pi by 4 in here it said it had a height of 1. So I'm going to use the same scale that I did last time. So we're going to leave pi by 2 for a second because he's weird. We're going to go to 3 pi by 4. That's going to be this guy here. And then it had a y value of -1, 0 at pi, and then over here at 5 pi by 4, we're back up at 1. Again, something weird is happening at 3 pi by 2. I'm going to leave it for a second. And then it's 7 pi by 4. Again, I was at -1, and then at 2 pi I'm at 0. So not a whole lot of information here. What's going to happen with those undefined sections? That means that my graph cannot exist at those undefined sections, right? That means there's no possible y value. So what I'm going to see is a vertical asymptote at all of those undefined values. And you can take a look at this on Desmos and scroll around and zoom in and all that good stuff so you can get a better picture of what this looks like. But the tan graph is also periodic in that it does repeat itself. So it's the same section of the graph and it just keeps repeating. It repeats within these vertical asymptotes. So you're going to see that the vertical asymptotes exist. On our graph, it's every 6 squares. I'm going to have a new vertical asymptote. I'm going to be thinking of this point here in the center of the vertical asymptotes as like kind of the center of this curve. And what's happening here is I'm just going up and getting closer to the vertical asymptote and then going down on the left and getting, oops, don't curve back over yourself. That doesn't make sense. All right, there we go. So that's going to be my tan curve, and that whole thing is just going to continue to repeat. So I'm going to have another vertical asymptote here, and then repeating going backwards as well. When you draw the tan graph for me, if you were asked to draw it, you would use a ruler for those vertical asymptotes, and I would want to see them placed on your graph. these kind of sections of the tan graph remind people sometimes of a cubic graph. It's similar, but there's no flat section at the origin, or sorry, at a height of 0 like a cubic graph has. So you'll just repeat yourself. And then we're going to summarize the properties of this graph. All right, so what I've drawn here, I've got 5 full cycles drawn, is what I would see here. So I've got, remember, a cycle is just a complete section of the graph that repeats itself. So I'm going to look at the properties of tan theta, and the period is the length of any one of these cycles. So remember, the length of a cycle was 6 squares on my graph, and if I go back to the origin and count over 6 squares, I notice that I end up right at pi. So I know that the period of this graph is pi. I'm repeating myself every pi. And then the axis of the curve, I still am going to talk about an axis, and it's going to be where is the center of that curve. Vertically, the center is right here on the x-axis again. So the horizontal line that cuts through the curve is at y equals 0. Now the amplitude is like the distance, again, from the axis of the curve to the top of the curve, or from the axis to the bottom of the curve. That doesn't make sense because there is no top or bottom of the curve here, so the amplitude is undefined for the tan curve. The maximum and the minimum values, again, there are none. There's no top or bottom to this graph. Now the vertical asymptotes, couple different ways that you can write this. I'm going to write it in a way that you'll understand it, and then one of your homework questions actually helps you to come up with some mathematical expressions. And you've seen some similar things. I think in Unit 1 we looked at a few of them. So the vertical asymptotes are vertical lines, so it's going to be the x equals, or in this case, theta equals. Where are the vertical asymptotes? So I can see here there's one at positive pi by 2, and there's another one here at negative pi by 2. So I'm going to say there's a vertical asymptote at plus and minus pi by 2. And then going out from there, there's another vertical asymptote. Here it is at 3 pi by 2, and then there's the mirror image of it over here at negative 3 pi by 2. So again, plus minus 3 pi by 2. And then if you keep going, so notice here we have 1 pi by 2, 3 pi by 2. The next one is at plus minus 5 pi by 2. You can see that on the graph. And then we'll just do comma dot dot dot. Hopefully you can kind of see the pattern there. The next one will be 7 pi by 2, then 9 pi by 2. And from this we can come up with the domain. So the domain is super complicated for the tan graph. It was nice and simple for sine and cos. Here, theta can be any real number except theta cannot be any of these vertical asymptote numbers. So I'm going to repeat what I did above, and I'm just going to say theta can't be plus minus pi by 2, plus minus 3 pi by 2, plus minus 5 pi by 2, and then comma dot dot dot. Not the best mathematical way to write this. All right, and then how about the range? Well, the range is actually the simple thing for the tan graph. There are no limits to the y values because it goes up and down forever to infinity. So again, you are going to come up with simplified expressions. There's not really any homework today. Your homework is to memorize these 3 parent functions in radians. So you already knew the sine curve and the cosine curve from last year, but we need to know them in radians now. I have assigned some challenge questions for today's homework. So you're memorizing the key points of these curves so that you can sketch them. We're going to do transformations in the next lesson. But in the challenge questions, number 2C will help you come up with expressions for the vertical asymptotes and the domain that are just a little bit neater. All right, enjoy that homework, guys. Have a good day.